Greetings, the Astro 30 here, yet again, your crazy Australian idiot, and welcome back to AEL. No, I didn't mean that about the crazy Australian idiot. I am crazy and Australian, but not necessarily an idiot. Anyway, today I'm going to be looking at a interesting project that someone in the comments on a previous video brought up. Have I ever seen this? And I said no. So I went and checked it out. We're going to be looking at a discrete headphone amplifier designed by a guy named Ronald W. Anderson, and this was published in a magazine called Nuts and Bolts in September 2013. Now we ignore the picture here because according to this text down here, this is the picture that should have gone with this, and this picture was supposed to go with the last article published in August edition. Anyway, I've linked in the description the PDF to this, which is freely available. You don't have to pay for it. So you can check out the project. It's on page 28, and there's other stuff in there you may find interesting as well. So here's a look at the schematic to this amplifier, and one would be forgiven for thinking immediately that this is a typical Class AB amplifier with a quasi-complementary output stage. Well, it's not. Everything here is conventional, and it's using quite a few elements of Douglas self-design, like this emitter follower in the VAS circuitry here, and current mirror. But when we get to the output stage, if you look more closely, well, this is not quasi-complementary. This is actually a Class A amplifier with a current sink, and the LED is a dead giveaway on Q11 that this is a current sink, because the LED is being used as a voltage source to this. Now, what is a current sink? Well, it's the same as a current source, except it's in the negative path or negative rail of the circuit. So the way to look at this is, well, this is a current source up here because it's in the positive side of the circuit. So the positive side is source, the negative side is sink. So this, for all intents and purposes, is a current source to this output transistor. And what that does, it just maintains current, constant current, to this output transistor. So this BD139Q10 is the one doing most of the work driving the load. This isn't driving the load with any audio signal. It's just maintaining current to this output stage, which is actually a clever way of doing it. And I've never actually seen anyone do this before. Usually you find current sources and current sinks in the input stage circuitry or even the VAS circuitry, not in the output stage. Now, would this work on a higher powered amplifier? Probably. Is it practical? No. So I'm not going to talk too much about it. It's a pretty conventional design. We've got a long tail pair, current mirror, current sources, a current source for the VAS, and he's using 2N551 NPN transistors and 2N5401 PNP. I don't have either of those transistors, so for this low power, low current application, I can substitute these easily out for BC547 and 557 respectively. The only thing that this may cause is it may affect the overall total harmonic distortion figures of the circuit. Now with this LED, this is quite important. It needs to be a LED with a forward voltage of around 2.1 volts, because this voltage reference depicts what the current is going to be. And looking up further here at his pref board layout, or perf board layout, whatever you want to call it, he's just using what looks like a standard green 3mm 40 MCD LED. And I've looked these up on JCar. The forward voltage roughly is 2.3 volts, which is the ones I've got. And if you use a different color LED, well, you're going to get a different forward voltage. So yeah, you can't really change the color. So the forward voltage of this LED is quite important to get the correct amount of current flowing in the output stage. But the difference between 2.1 and 2.3, there's not much in it. So I'll try that particular LED and see if it works. I mean, if anything, either the circuit will work or it won't. And then I'll just try a different LED. So what I'm going to do is I'm going to breadboard this circuit up, and I'm going to run some tests. So I'll spend the next hour or so fleshing this out on breadboard, and then we'll come back once the circuit is assembled and start testing. Alrighty then, about an hour later, or close to it, yeah, about an hour, I've got the circuit fleshed out. So down here, these two transistors here are the long tail pair. These two transistors here are the current mirror. These three transistors here are the current source transistors. These two transistors down here are the bass. There's our voltage reference LED. It measures at about 1.8 volt, not 2.1. Yeah. And up here, this transistor is the output transistor, and this one is the current sink. Now, I'm going to do a preliminary test at plus minus 12 volts. The LED should light according to the instructions, and measure the output voltage on the multimeter. It should be close to 0 or up to around 30 millivolts is acceptable, apparently. So I'll turn the circuit on. No unusual current draw. LED is illuminated, so that looks pretty cool. You could use that as a power indicator as well, but it is an important part of the circuit, and don't change the color as I already stated. Looking at the output, we've got about 40 millivolts there. It's a little high, but that could also be due to the layout on the breadboard as well, and of course differences in transistors. But so far it looks like it's going okay, and if I touch the input with a wet finger, we can see it starts jumping around, and then we'll stabilize back out to roughly 38 millivolts. So I can see straight away it's working as an amplifier. So before loading the thing, I think the best course of action here is to hook it to an oscilloscope unloaded and just see if we're getting any signal output. Yeah, it doesn't seem to like that. It appears to be oscillating, so I might try putting some bypass capacitors in the supply lines and see if that disappears. But that's not right. If I go to times 10, which is not loading the amplifier as much, and then increase my voltage per division so we can see stuff, it is fairly noisy. But touching the input, yeah, the signal is moving around. So let me put some bypass caps in and see if that cleans that up. Okay, so I've got a couple of 100 nanofarad capacitors, one across the negative rail to ground and one across the positive rail to ground, and it's made a big difference. And back in the times 1 probe, we can see the signal's cleaned up quite considerably. If I touch the input, hey, we now have what looks like a working amplifier. I'll just check these heat sinks. They're cold, so it appears that's working fine, because when I actually connected the oscilloscope probe to the output in times 1, this transistor started heating up. But then again, it was oscillating. So I'm going to check that DC offset again now that I know the amplifier is not oscillating, which is probably why it was a high offset. And we'll just see what we've got now. It's actually dropped to 23 millivolts, which is considerably better. I'll touch the input again. That DC voltage is changing slightly, but it's not really significant. I don't know if I can improve that any further by adding some bulk filtering. That is putting two electrolytic capacitors in parallel with those 100 nanofarads and see if that brings the DC offset down. However, I might disconnect the scope and see if that changes the DC offset. No, it doesn't. Okay, so fine. Let me stick a couple of 100 microfarads in there and see what we get. Well, they're in, but it made no practical difference. But it is a good idea to include bulk filtering in the power supply rails just to bypass them correctly. As we can see, the DC offset didn't change much, but that's still acceptable. And as for the output, yeah, it's still amplifying. Right, let me connect a signal generator to the input and adjust the voltage per division so we can see an output. And we'll see how clean the output actually is. Oscillator is connected, providing a 1 kilohertz output signal. the amplifier is still unloaded, and we've got a nice clean output signal. I'm just checking the heat of the output transistors. They're not getting that warm, so it's perfectly acceptable at this stage. And that looks like the maximum output swing we're going to get before clipping, because there's clipping there. And so 7.35 volt RMS at the output, which is not too shabby. So I'm going to drop that down, and I'm going to start loading the amplifier. Now I need to do this a little bit more accurately, because the common range of headphones are 32, 64 and 120 ohm respectively. So somehow I've got to come up with a convoluted solution for loading it. So I might have to put several resistors in parallel to get the right resistance. So let me just go off camera and mess around. I want to start at 32 ohms to start with. Okay, so here's what I've come up with. I've got a 22 ohm 5 watt resistor in series with a 10 ohm 1 watt resistor, which is perfectly fine for this sort of amplifier because it doesn't produce much power. And that gives me 32 ohms. The circuit is currently on, just making sure that everything is connected. And we do have an output, but I'm not sure how much power this is going to produce. So that's the thing I want to find out. So I'm just going to do some, there we go, there's clipping. Alright, we're looking at 1.83 volt RMS, which into 32 ohm headphone speakers is pretty loud. So I'll just calculate what that is in wattage. About 100 milliwatts, which is, yeah, it's reasonable I suppose. Just going to check everything. Load's not getting hot. Transistors are not getting hot. Okay, so I'm going to kill the oscillator now. Now I've got to make 64 ohms, which is going to be a little bit more of a challenge. I reckon I can come up with something. That's highly inadequate. I've got two half watt 33 ohms in series. And that should give me an equivalent resistance of around 66 ohms, which is about as close as I'm going to get it with my standard values that I've got. It's not ideal, but for this quick test to measure its power output, it will be sufficient enough. Okay, turn the circuit back on. No unusual current draw. We still have a power output, which is good. It's going quite a bit further now. Just got to be careful of those resistors. So that's without clipping, so we got more like 2.6 volt RMS. Not much difference, about 105 milliwatts. Okay, so we're at 120 ohms now. Okay, turn the power on. No unusual current draw. We have an output. And out of clipping. Looks like we've got pretty much consistent results here in power output, so we're at 2.77 volt RMS. That's actually more like 63 milliwatts. Okay, so when it starts getting up in higher impedances, it is starting to lose a bit of power. For shits and giggles, 240 ohms. Got two 120s in series with each other. Let's see what we get. Power on. Increase the oscillator. Well, that's interesting. The higher we're going in impedance now, looks like we're actually getting more output. Assuming that I've connected it correctly, of course. Which it appears that I have. Okay, so where are we? There's clipping. 4.43 volt, but yeah, okay, let me calculate it. It's actually an improvement over the 120 ohm load. It's actually 81 milliwatts. I wonder if I can get this close to 600. I've got a 330 ohm 5 watt in series with these two 120 ohms in series. That gives me a resultant resistance of 570 ohm, which is about as close as I'm going to get. Welcome to AEL. Everything's an exact science when doing measurements. No, it's not. Turn the power on. We've got an output there. Crank him up. Very good. So 6.46 volt RMS. And again, not very impressive. It's actually a little less than the 240 ohms. So, okay. Alright, so these are my results. At 32 ohms, we've got 103 milliwatts. At 64 ohms, or close to it, got 105 milliwatts. At 120 ohms, we've got 63 milliwatts. At 240 ohm, a little more, 82 milliwatts. 73 at 570 ohms, so it'd be probably close to the same at 600. So averaging those out, ignoring the 120 for the moment because it seems to be the lowest, this thing would produce around about the 83 milliwatt range into most headphones, which is still significantly loud, mind you. Now the next burning question that people may ask, why go to all this trouble when you could just use an op-amp based solution? Why have all this discrete circuitry? Well, some people complain with headphone amplifiers using op-amps that there's just way too many transistors in the signal path, which I agree. The NE5532, for instance, has quite a fair few transistors in the signal path, mainly for its short circuit protection and all that sort of jazz. But with a discrete design, you can actually get the distortion fairly low, which is what we're aiming for. Plus it's Class A versus Class AB. The reason why we'd use Class A is because it doesn't suffer from crossover distortion like Class AB does. And someone in the comments of another video said Class A is dead. Like, dude, what? What are you talking about? No, it's not. I agree that Class D amplification is the way that we're doing it now, like with subwoofer amplifiers and stuff like that. There are still some people that build amplifiers in Class AB format for subwoofers and stuff like that. But Class A, it's still valid. It's not dead. And there are still some enthusiasts out there that swear by Class A as because of the fact that it does not suffer crossover distortion. So yeah, I mean, yeah, sure, they're higher biased, they generate more heat, they're less efficient, but they do give good sound quality. So that's what I'm sticking with, and I'm sticking with it. I'm not going to argue the point in comments on YouTube about Class A being dead. So the next thing to do would be to connect this up to a proper load such as a headphone set, and well, I kind of use one channel, that's alright, and just see how it sounds. I'll turn the oscillator down now. So I'll just use the oscillator for the first instance here, and you know, to see if it's noisy or what have you. Got my Stadium HP Studio headphones hooked up just on the left channel to the circuit. I believe they're 64 ohms, they may be 32. I honestly can't remember. Now the scope is still connected, so I can hear something. Oh yeah, that really drives it into distortion into the drivers. And it is pretty loud from where I'm standing. And yeah, there is no way that I can put that up to my ear, because that'd be deafening. So that is pretty loud. I've turned it down. We can't see it on the scope anymore because we're out of range. But if I lean over the camera, there we go. I could probably do with a Zabel network as well, but it is running into a pair of headphones, but I guess it would be prudent to actually measure what the impedance of my headphones are. Well, at least it's DC resistance anyway, 32 ohms, so yeah, they're 32 ohm headphones. I was wrong, but I admit when I'm wrong. I could have sworn they were 64, but yeah, as I said, 32 ohm headphones in the cheaper ones, because they're only like 30 bucks, I think it was, from JB Hi-Fi, are the more common ones on the market. Well, them and 64. So, okay, very, very good. Very, very good. I was going to say the LED has stopped illuminating, but that's because the circuit's off, you dickhead. I forgot I turned it off. Right. Okay, Batman, what's next? Okay, well I guess I should pump an audio source through the amplifier. I'll actually disconnect the oscillator. I want to just do a basic noise floor test into the headphones directly, just to see if I can hear any, like, you know, circuit noise. I'm guaranteed that I will, because, well, it's all open circuitry here. So the oscillator is disconnected, so I'll reapply the power. Of course, the DC offset, because I missed the second power switch. There is a slight buzz in the headphones, but nothing really that loud. Okay, so I'll hook up an audio source to it now, play some music, which you probably won't be able to hear that well, but I'll do my best to make it audible. Okay. Whoa. Quite a bit of noise there on the scope that's coming off the computer's output. Although I can't hear it in the headphones, which is interesting. Alright, I'm going to play a track. It is coming out. Might turn that down. See if I can get it a little bit more louder than that. Now that's fairly loud. So I wouldn't be able to wear that on my ears, because that would be fairly painful. Okay, that's enough of that. All the frequencies are there. Well, I guess it's not that loud, but it would give me listening fatigue after a while being at that level. It's just a bit noisy, well, on the scope anyway. So I call that a success. I want to thank Mr. Bun 9 Pipe 3. I don't know if that 9 Pipe 3 is supposed to represent another letter or anything, or what it actually means, but Mr. Bun anyway, for pointing this circuit out to me, which I missed. I don't think we actually get the Nuts and Bolts magazine here in Tasmania, which is probably why I've never seen it. It is an Australian publication, but yeah. But it's sounding alright, it's working okay. Could this circuit be improved? Yes, most definitely. But for the average output power we're getting, which is around about the 85 milliwatt range into average loads, it's not bad. It can certainly amplify from a line signal with a volume potentiometer in between just fine. So yeah, you can amplify a CD player, tape deck, computer, whatever. But I'm going to leave this video here because I think I've done enough extensive testing on this and I'm pretty happy with the results and the fact that it worked first time. They are slightly getting warm, so these do need these two heat sinks on here. Otherwise you will end up damaging the transistors. But it does work with the substituted transistors, BC547, 557 respectively. However, that may affect the DC offset because of the chosen transistors, different characteristics. Also the distortion figures. He measured it at around about 0.001%, I think it was in the text there, maybe 0.0001% at 1 kilohertz at 32 ohms. So anyway, I've been the Astro 30. If you've enjoyed this video, please give it a big like down below and subscribe and comment if you haven't done so already. Cheers guys, I'll see you in the next video.